You've seen it 1,000 times, right? A stone hits a calm pond, and these beautiful ripples spread out. It seems so simple, but what's really happening in that water is a secret that explains how energy moves all around us, from the quietest sound to the shaking of the entire planet.
So let me ask you this. When you see that ripple, it looks like the water itself is moving outwards from the center. I mean, that makes sense. But if you were to put a tiny leaf on that water, you'd notice something strange. It mostly just bobs up and down, right in the same spot. So if the water isn't traveling, what is?
And that's the big secret. The water particles, they're just the messengers. They're jiggling up and down, but they're not really going anywhere. What they're doing is passing energy along from one particle to the next, almost like a microscopic game of hot potato. And that transfer of energy through matter, well, that's what a mechanical wave is all about.
Okay, so here's the official definition. You've got oscillation of matter, that's our jiggling particles, and transfers energy, that's the whole point of the wave. But the most important part, the real key here is physical medium. Think of it like a highway the energy has to travel on. Without the road, the energy has nowhere to go. And that one rule, it changes everything.
So here's the crucial point, the absolute golden rule. No medium, no mechanical wave. It's what makes them completely different from electromagnetic waves. You know, like light or radio waves. Those guys can just zip right through the vacuum of space, no problem. But for sound to get to your ears, or for a ripple to cross a pond, there has to be stuff for the energy to move through.
All right, so now that we know what a mechanical wave is, let's get into the two main ways it can actually move through all that stuff. You can think of it like the wave's signature dance move.
First up, we've got transverse waves. The best way to picture this is to imagine flicking a rope that's tied to a doorknob. The wave of energy travels straight towards the door, but the rope itself is moving up and down, right? It's moving perpendicular to the energy's path. This up and down motion creates those classic wave peaks we call crests, and the low points, or troughs. And because they need this kind of rigid, shearing motion, you're really only going to find them in solids, or right on the surface of a liquid.
Now, the other main flavor is the longitudinal wave. And for this one, you gotta picture a slinky. If you push one end of it, you see that pulse of energy move down the spring, right? The coils themselves bunch up and then spread apart, all in the same direction the energy is traveling. Those bunched up spots are called compressions, and the spread out parts are rarefactions. And the most famous example of this, sound. It's just a longitudinal wave compressing and rarefying the air all the way to your eardrum.
So when you put them side by side like this, it's pretty clear. The main difference is that particle motion, perpendicular versus parallel. But honestly, here's a pro tip for you. Just look at the medium. If a wave is moving through a gas, like the air all around us, you know for a fact it has to be a longitudinal wave. And that little rule, it becomes incredibly useful.
Okay, so let's take these basic ideas, ropes and slinkies, and scale them way, way up, like planet-sized up. Because it turns out that understanding these two simple wave types is kind of like having a superpower for decoding the secrets hidden deep inside the Earth itself.
I mean, this is a fantastic question, isn't it? The deepest hole humans have ever drilled is only about 12 kilometers deep, but the Earth's core is nearly 3,000 kilometers down. We've never seen it, we've never touched it, so how on earth are scientists so sure that it's a giant ball of molten metal? Well, the answer comes from earthquakes.
You see, earthquakes create two main types of waves that travel right through the planet. First, you get the P waves, or primary waves. They're longitudinal, so they're the all-terrain vehicles of waves. They can push through solids, liquids, and gases. Then, the S waves, or secondary waves, arrive. They're transverse. And remember our rule about transverse waves? They need a rigid medium. They can slice through solid rock no problem. But they are completely, totally stopped by liquid. And that, my friends, is the smoking gun.
And this leads to something amazing. After a big earthquake, scientists with seismographs all over the world record these waves. And they see the P waves arriving pretty much everywhere. But for the S waves, there's this huge dead zone on the opposite side of the planet where they just never show up. This shadow zone is the evidence. The only possible way to create a shadow that big is if the S waves are being blocked by a massive sphere of liquid deep inside the Earth. And that's how we discovered our liquid outer core. Just incredible.
So those P and S waves are awesome for telling us about the deep interior, but when they finally reach the surface, they mix together and create a brand new hybrid type of wave, and it's the one that we actually feel up here.
Yeah, when all that energy from the P and S waves hits the ground beneath our feet, it kind of gets trapped there. It creates what we call surface waves. And these things are complex.
They're a mix of the up and down motion of a transverse wave and the back and forth push of a longitudinal wave. And it all adds up to that rolling or swaying motion of the ground we associate with earthquakes.
So why does this matter so much? Well, even though the surface waves are the slowest and the last to arrive at the party, they pack the biggest punch. All their energy isn't spreading out deep into the earth. It's focused right where we live. This gives them a much larger amplitude, which causes the most violent shaking and, sadly, the vast majority of damage to our buildings.
So you see how it all connects? That simple, tiny ripple in a pond operates on the very same physical principles as the seismic tremors that can level entire cities and literally reveal the structure of our planet. It's all just energy moving through matter, shaping our world in ways both incredibly small and absolutely catastrophic.
So, I'll leave you with a final thought to chew on. We hear all sorts of thunderous sounds from deep underwater, right? From whale songs to volcanic eruptions. We also know that sound is a mechanical wave. So, given that we know for a fact that transverse S waves can't travel through liquid, what does that tell you about the nature of those sound waves moving through our oceans? The rules we just covered give you the answer. They're at play all around us all the time.